All right. We are back for more fun. Maybe. All right. We have any questions?
Yeah, we were going to we were interested in looking at from fall 20
Uh-huh.
part 2. It really doesn't matter which
Okay.
version.
Part 2. I got one right here. Let me show you what I have. And let's do it this way. Okay, part 2. Looks like we got part 2 continue. We got 2 parts of part 2. So we got the alkene part of part 2 and the alkyne part of part 2. And you will have something similar. So what do we have here? Let's, there's Snippy. And there we go. I think if we make it, spread it out a little. There we go, fall 20. So where are we supposed to start? Okay, we're supposed to start over here where it says start here. On our test, we have to know that deuterium is just a hydrogen atom that has the same chemistry, just weighs one more atomic mass unit. Tritium has one more neutron in its nucleus than deuterium, and it weighs 3. And we need these isotopes for studying reaction mechanisms. So we can differentiate hydrogens from, new hydrogens from old hydrogens is basically what we can do. So let's deal with a simple one first. HCl, that's our first reaction we studied. The major will be the Markovnikov with the more electronegative halogen here, less electronegative hydrogen there. And that's product D. I'm better at drawing my cyclohexanes like that, so a little rotation going on, but I think we can get past it. And we have a new Cl right here. Let's go with that. And we don't have to show the new hydrogen, but it's right there. And here, the anti-Markovnikov product. The other part of the alkene was here, one away, vicinal to where we put the first chlorine here. And there we go. And D and E, and we're going to go for, let's do F in a second. D2 and PT is one of the later reactions in chapter 6. It's called hydrogenation. Here we're using deuterium so that you can show me that this is one of the reactions where there is syn stereoselectivity, which delivers the 2 new deuteriums to the same side of the ring. And you show me that by doing either wedge or dash for the deuteriums. I'll go with wedge, new deuterium here. Now, if we use just H2 and PT, we wouldn't be able to tell they were syn, because on this carbon here, there'd be 2 H's, and you wouldn't be able to tell the difference. But deuterium is different than hydrogen, even though the chemistry is the same. All right, hey, maybe we should have started with ozonolysis right here. Product B, there's the side product with the sulfur. We learned we're going to cut it right there. And here I will avoid rotating the ring here so that I can use my new skills, double O there, and keep drawing around the ring that used to be there. Got a methyl there. And we're up to here with the isopropyl. And we'll try to squeeze in the carbonyl without touching the other carbonyl. Doesn't look pretty, but it's got it. Yeah, that's a ketone. Not the greatest looking ketone, but it is. And there's an aldehyde. And what happens with product A? Well, this is the halogenation reaction where we get two new halogens and it goes by way of a triangle reaction mechanism. So there's a backside attack and all that good stuff. And yeah, you guys are pretty nice to me. You didn't notice, or you noticed, but you didn't mention my methyl's missing here and here. Thank you. Yeah, I forgot those methyls entirely. They didn't change. Now I notice, and we got this here, isopropyl down here, and bromines. One has to be a wedge, one has to be a dash if you want both your points. You get 50-50 mix of wedge here, dash here, and the enantiomer, which would be dash up here and wedge down here. So anytime there's 2 points, you probably have to think about stereoselectivity. That's just something to keep in your mind. All right, so we've done these guys and this guy. We got to go in the middle here. We'll put F here. And F is worth 3 points. Yes, stereochemistry is important. So let's just put F with a red letter. And here's our ring. Methyl up here, isopropyl here. This is one of the later reactions where both the B and the H get delivered at the same time. So there has to be a syn addition as well, just like the D2PT. And this part of the reaction is Markovnikov. The more electronegative H on the more substituted carbon. And if you want to get 2 out of 3, do this. Put BH2 here. You'll get 2 out of 3 for that answer. I know you want 3 out of 3. So you're going to put BR2, and you don't get 3 out of 3. Still get 2 out of 3. It's fine to use R groups, but if you haven't defined them, don't expect any credit for them. You have to circle exactly what you intend R to be and because you're showing me you know this thing happens 3 times. Each bond from B to H reacts with a separate alkene. So its stoichiometry is 3 alkenes for 1 BH3. And you're going to carefully circle everything except for the BR2. And I want it to be very clear. This is our first time doing these circles. And I am never going to take it easy on you. If you're going to do circles, you're trying to save time, you better do it properly. So everything up to, but not including the B and the other 2 R groups, is called R. That means there's 3 of these on boron. Think about it. If each R is the circle, the circle is the 3rd one. So there you go. You got your 3 points now.
So to get our points for like when there's an R group, we have to like define what the R group is, and like in this example,
that's the fastest way. The other way is to draw this blue thing 3 times each on the boron. I don't think you want to do that, right?
Okay,
It's another way to do it. You could draw each bond from boron to the 2nd carbon up here with a wedge, and the 3rd carbon up here with another wedge. But I don't think that's using your time wisely when you can use a short form as long as you correctly label it. And it looks like this product over here comes from the enantiomer. You realize you made this 50% and the enantiomer 50%, which was dash dash. So this product we have up here from the original question had dash dash for the H and the OH. I know it didn't show a dash here, but if the isopropyl's on a wedge, then there's an H there that's on a dash. And now the question is, how do you replace the bond from C to B with a bond from C to OH? And that's called oxidation. And we can just put the oxidation molecules here. Reagent X, hydrogen peroxide. And this works for both the chapter 6 hydroboration and the chapter 7 hydroboration. The second step has the exact same reagents each time. This is the chapter 6 boron reagent. Chapter 7, where you're reacting alkynes, you should use HB-Sia2. That's the disec isoamyl borane, works better with triple bonds than this BH3. So there we go. We got that. That's another point for reagent X. Now we're going up here. We're doing the oxymercuration step and then the demercuration step here. There's no mercury here, but there's this T for some reason. Okay, oxymercuration is another triangle reaction, so I better see wedge dash product. There is, oh, interesting. Yeah. There is no, is there a mistake? Oh, reagent Y. That's a, yeah. Where's reagent Y? Did I fool myself? Yeah. I'm looking around. I'm looking for reagent Y. Oh, you got to provide reagent Y. No, geez. It says right here, provide reagent Y. I can't read. Okay. So it's an oxymercuration reaction. The mercury comes from here. Where's the oxy come from? Well, normally we use water, but it doesn't have to be water. It can be an alcohol instead. And how do I know this is the alcohol instead example here? Well, during oxymercuration, you're going to put a mercury on the less substituted carbon because mercury is less electronegative than oxygen, and an oxygen on the more substituted carbon. The oxygen's a wedge or a dash. If you chose a wedge for the oxygen, the mercury must be a dash. And look, we have a big fat clue over here. Oxygen on a wedge. The mercury gets replaced by something in demercuration, and that something here is T. That's during the reagent Z step. During the formation of product G, that's going to be a mercury exactly where you see the T. So I'm going to draw product G first, and then loop around for the two reagents Y and Z. So here's product G. We need a mercury here, and it loses one acetate on its way, and we need the oxygen here. That's the exact oxygen that you see in the end of the sequence there. And don't forget the isopropyl. Don't forget the methyl. I forgot it earlier, but I've made a good comeback. So that's product G right there. How'd you get that O isobutyl on there? Well, I don't think anybody would have trouble if this was an OH telling me it was water that put it there, because that's the first one you learn during oxymercuration. Water, you keep one of the OH and you stick it on the carbon, and the H gets lost to acetate. Well, here, you're not keeping OH, you're keeping OR. So reagent Y has O isobutyl, and it lost its H to the acetate ion. So isobutanol was used instead of water. You got exactly the same result. And reagent Z is normally NaBH4 to get rid of mercury. Please don't write NaBH4 here. NaBH4 replaces mercury with an H. Are we replacing mercury with an H? No, we're replacing mercury with a T, tritium. It's an isotope of H. Show me you know that you can use isotopes in the same fashion you used an H. NaBT4 would be reagent Z. And there we have, I think, did we do everything? Yeah, product F's down here. Reagents X here, just making sure we're clear. There, saving. And when we come back, do you want to do the other one that started with the alkyne in the middle? Sound like a good deal?
Part 2.
Yeah, the other part 2. We'll do that on our when we come back. And I'll see you then.